Okay, lesson 7.6. This is the end of the unit. We've done derivatives, so guess what's next? You betcha. Integration involving the natural log function. Now, before we actually go ahead and do some of these questions, I hope you remembered that the derivative of natural log of x, and yes, you can have x or the absolute value of x, it's the same thing, it's 1 over x. Okay, so reversing it, because the integral is really just the antiderivative, the integral of 1 over x is the natural log of absolute value of x plus c. Okay, and then of course if you have that chain rule feature, you have to have the u prime, a little bit more complicated, but still the same thing. Remember this. Okay, now I know many of you were thinking, hey, I remember doing the antiderivative, and it's a power, so this is x cubed over 3 plus c. Even this, the integral of x, right, using the power rule. So you might be thinking, how come I can't use the power rule for 1 over x? Well, remember, that's x to the negative 1, right? And if I asked you to add 1 to the exponent, that's x to the 0, but then you're dividing by 0. You're like, what? What's up with that? So once again, that doesn't work. And by the way, the power rule was this. But there was a caveat, provided that n was not equal to negative 1. So now you know when the power is negative 1, the antiderivative is just the natural log of the absolute value of x. Okay? You might be thinking, Mr. Lee, why do we have to have that absolute value sign? Why can't it just be regular x? Good question. Remember the issue with natural log, though, and all log functions? It's only valid when x is bigger than 0. So why do we do the absolute value of that? So we can actually protect the domain. Okay. So when you evaluate, you actually get a number. You get a number. Remember, the natural log of a negative doesn't exist. Okay, that's enough the preamble. Let's actually do this. Number 1, let's integrate negative 3 over x dx. Hey, I see negative 3 as a constant. I hope you remember the integration rules. We'll just take it out. And then you're just asked to do the integral of 1 over x dx. And yes, that's just the natural log of the absolute value of x. And then this is an indefinite integral, so plus c. Cool. For number 2, you're like, I don't see anything with just x in the denominator. That is correct. Remember what other integration techniques we used? How about u substitution? Remember that? So if I let u equals to p squared plus 1, du dp is equal to 2p, and then du over 2p equals to dp. Remember all this stuff? You're like, no, I forgot. Well, here's a chance to review. This then, of course, equals to p over, and that whole denominator is now u. dp just becomes du over 2p. This works quite nicely because the p's then divide each other out. That half in the denominator can be a constant that I take out. And now, do you see the 1 over u? And so the antiderivative of that is just the natural log of u. I'm going to skip a step and replace u with our p function, because that's what we started with. And then don't forget plus c. That's our answer. Okay. So for number 3, can I ask you to try that, this one? You're thinking, where's my natural log, or where's my 1 over x? You're right, it's not there. You're going to have to do it and find it somehow. Go ahead and let u equals to t cubed minus t squared. I like that. How about you try the rest? Okay, it's pretty much the same as number 2. Go. I see a factor of 3 I'm going to take out of here too. I hope you're not waiting for me to do this. This just becomes 3 over u du, and then I can rewrite this as 3, 1 over u du, and just like number 1, the integral of 1 over u is just the natural log of the absolute value of u plus c, and I should have just done that in one step because I could have replaced u with t cubed minus t squared plus c. Done. Alright, now things get more complicated. Looking at examples 2 and 3, I hope you can see that the degree of the denominator was always 1 more than the degree of the numerator. But what happens when the degree of the numerator is bigger or equal to the degree of the denominator? Well, then we actually have to employ long division, yes, stuff from pre-calculus 12, to split the fraction up. So I hope you remember how to do long division. I will do it here for you. You take your divisor, x plus 2, you're dividing it into your dividend. You ask yourself, x squared goes into x squared how many times? And I hope you remember it's 1, so x squared times 1 is x squared. Then you just have to multiply the 1 by the x plus 2, and put the answer underneath, and then like division, you subtract. X squared minus x squared is 0, that's always what you want. Oops, I made a mistake. It's not 2x. Oops, oops, oops. It's 2. Negative 4x minus 0, that's negative 4x. And then 2 minus 2 is 0. Perfect. What does this mean, though? Remember, 1 is your quotient. That's your remainder. So really, I can rewrite this question as 1 plus the remainder, negative 4x, all over x squared plus 2 dx. Okay? It's also kind of like the idea where you took a fraction like 55 over, I don't know, 9, and then you try to write that as a mixed number. So 9 goes into 55 how many times? 6 times, and then there's 1 left, 1/9. Okay, same idea. Why is this helpful? Because now you can break this up into 2 separate integrals, the integral of 1 dx. The plus and the minus will become a negative, and you have 4x over x squared plus 2 dx. And now go ahead and integrate. I like the first part. The integral of 1 dx, just x. This next part, don't like so much. How come? Well, now this is a degree of 2 on the bottom, degree of 1 on the top. Just like the questions from above, you're thinking u substitution. Du dx is 2x. Dx is du over 2x. Go ahead and u sub it away. You remember u substitution? Good stuff, good stuff. Yay, yay. Oops. That simplifies to just 2, so now we have the integral of 1 over u du. That, of course, is just natural log of u plus c, and I will replace the u with x squared plus 2. Are you wondering about something? Are you wondering why I didn't use the absolute value signs this time around? You could. I'm just saying you don't have to. Think why? Can you think why? I'll leave that up to you to think about. Okay? Alright. So, one of the methods, if you're looking at rational functions with just powers or degrees in the numerator and denominator, then you can use these methods. But if you're dealing with something like this where natural log is a function, then doing long division might not be the best thing to do. What is a good suggestion is to just let u equals to ln x. So like in example number 5, if you let u equals ln x, du dx is just 1 over x, or dx equals to x du. And if you make the change now, the numerator becomes u, You still have your x, but your dx now becomes x du, and that's beautiful because your x is now divided out, and you're just left with the integral of u du. A nice simple power. Add 1 to the exponent, divide by the new exponent, don't forget plus c, and then resubstitute back in u. Done. Okay, you try number 6, because it's very similar to number 5. Maybe not letting u equals to just ln x, but the entire thing in the bracket would be a good idea. The derivative of 2 is still 0 anyway, so no biggie. Negative x du now equals to dx. Making the substitutions, let's see what happens. 1 over x, u cubed, dx now is negative x du. Divide out. Ooh, look what you see now. Another power. Now you're ready to anti-differentiate. U to the negative 2 over negative 2 plus c. Lots of negatives, don't freak out. That's quite alright. Ta-da. Yeah. Alright, one last one that I will do with you, and then it's time for you to do some practice again. How do we even start this one here? If you're thinking, maybe I'll let u equal to the entire denominator, sure, try that. Remember, that's the same thing as x to the power 1/2, so the derivative using power rule, 1/2, x to the power of negative 1/2. And then if I wanted to solve for dx, I guess I get du with a 2 on this side. And if I wanted dx by itself, I would move the x to the negative 1/2 to the other side, so that becomes x to the power of positive 1/2. And that's what I would have. Okay, let's try to do u substitution now. So 1 over u, and dx becomes 2, x to the 1/2 du, and now you're like, that's a problem. I have nothing to divide out the x to the power of half. What to do? Remember what we can also do with this expression. We can move this around, perhaps write down u plus 1 equals to the square root of x. And once again, the square root of x is just x to the 1/2, so bam! We now know that the x to the 1/2 can be replaced with u plus 1 du. Nice! So let's see, that's 2u plus 2 over u du. So I distributed that and put it in the numerator. Be nice if you can separate this into 2 separate functions. I'm thinking now 2 over u du plus 2 over u du. The first one just simplifies to 2. Nice. The second one, I can take out the 2. Nice. Time to integrate. Time to substitute. Nice. Done. Now just to let you know, this can be written as 2 2 root x minus 2. And that minus 2 is a constant, and so is this. It's a constant, so you could combine it together. Whoa. You could combine it together and make your answer like this. 2 root x minus 2 ln absolute value root x minus 1 plus c, because a number plus a constant is still some sort of constant. That also works. Okay. Integration much more trickier. I would like you to try more problems. Yes, do all 1 to 14 for sure. Please do those. But not only that, also try questions 30 and 31. That's your assignment. Get to work. See you in class.